Welcome to Frequency Response Square Wave Analysis. Today we're going to take a look at the low frequency cutoff formula. We're going to derive it from some formulas that we should already be familiar with. So here's our square wave analysis formula for calculating the critical low cutoff frequency. And that formula is fractional tilt divided by 2 pi pulse width. And we're going to use the X sub C, the capacitive reactance formula, and the capacitor voltage charge formula to derive that formula. So here's an image that I grabbed from my oscope, and I'm kind of zoomed in on just the top part of the square wave. And we can see that we've got two different voltages here, and that's giving us our tilt. We can also see that the pulse width is defined as time. The x-axis is time, and the y-axis is voltage. Okay, so we're looking at our waveform, and we should observe that between V1 and V2, it looks like a capacitor discharging. And so if we observe that and we're like, okay, that looks like a capacitor discharging. And now we can relabel or reassign those voltages. V2 would be VC and V1 would be the V initial. And that kind of gets those in terms of our voltage charge formula. Now we're going to take a look at the fractional tilt formula, which is V1 minus V2 divided by the average pulse amplitude, or delta V divided by the voltage average. That gives us our tilt. Now if we take the fractional tilt formula and put it in terms of our voltage charge formula, or our capacitive charge formula, we get V initial minus VC divided by, if we want to take the average of that, it would be V initial plus VC divided by 2. And then we can simplify that as 2 times the quantity V initial minus the VC divided by V initial plus VC. So now we've got our fractional tilt formula in terms of the VC formula. So let's see if we can go ahead and assign, we're going to assign a 10% tilt and solve for VC. And this slide shows you the algebra for solving for VC at a 10% tilt. Now let's do a little work back on our VC formula. We've got our VC at a 10% tilt. Let's start with our initial formula. VC equals V final minus V initial e to the negative time over RC. And because we're operating in the discharge, we're looking at a signal that's going down. It's a discharge, so the V final, we're putting in zeros for the V final. That leaves us with VC is equal to V initial e to the negative time over RC. So now let's substitute in our 10% fraction or 0.1 fractional tilt formula in for VC. And then that gives you the formula that you see there, all the way down to the natural log of 1.9 over 2.1 equals negative time over RC. We're going to do more work on the next slide. So we've got our natural log of 1.9 divided by 2.1 equals negative time over RC. Simplify that as RC equals T over 0.10083. Okay, now we're going to point out, look at time here and the correlation between pulse width. So now we can substitute in that. The other thing that I observed here is 0.10083 looks pretty close to 10%. So the speculation is RC is equal to pulse width divided by fractional tilt. Now, I wasn't totally sold on this, so in the next slide I ran all the numbers for 5% tilt in order to see that that number comes out approximately equal to 5%. So let's take a look at the next slide and see if that comes out like we are predicting. So here's the math with a 5% fractional tilt. So we've got 0.05 is equal to all the stuff we did before, and you end up with natural log of 1.95 divided by 2.05 now. And you see that when we take the natural log of that, we end up with that 0.050104, which is very, very close to our fractional tilt. And so now we look at those two relationships, and you could run more scenarios if you want to, just to double, triple check. But it looks like RC is in fact equal to pulse width divided by fractional tilt. Now that we've solved for RC in terms of pulse width and our fractional tilt, our square wave, we can look at our frequency cutoff low formula and derive that from, we know at that frequency X sub C, the capacitive reactance is equal to the R Thevenin that reactance, the resistance that reactance sees, the R Thevenin. And so if we manipulate our X sub C formula, we can substitute in the R, we end up with frequency critical or frequency cutoff low is equal to 1 divided by 2 pi RC. Now we've got RC in terms of square wave, pulse width divided by fractional tilt. We're going to substitute that in for the RC. That gives us frequency cutoff low is equal to 1 divided by 2 pi times pulse width divided by fractional tilt, which simplifies to our final formula. Frequency cutoff low is equal to fractional tilt divided by 2 pi pulse width.